This is Kevin Postman. Kevin is at Bigelow Laboratory, and he works in Dr. Stephen Archer's research group studying air-sea interactions and the processes that influence the exchange of gases between the ocean and the atmosphere. Kevin received his Bachelor of Science at Rochester Institute of Technology, studying the relationship between livestock runoff and antibiotic resistance in the environment, and he earned his Master's of Science at Cornell University, researching environmental microbiology and human impacts on biogeochemistry. Kevin lives in Bremen with his wife, Dr. Julie Brown, who is also a scientist at Bigelow, and their 2 children. You guys solved the 2-body problem. That's awesome, wow. It's 3-body problem, should have been your question on here. Anyway, sorry. Okay, so Kevin's pop culture is The Dispossessed by Ursula K. Le Guin, and his title here is The Mosaic Expedition, A Year in the Arctic Ice.
Okay, so today I'm going to be introducing to you a project that is going to transform our understanding of climate change, its impacts on the Arctic, and the implications for the global climate system. The Mosaic Expedition, the largest Arctic expedition in history, in which hundreds of scientists from dozens of institutions spent months aboard this ship, making measurements for months on end as it drifted from one side of the Arctic to the other. And I'll touch a little bit on the work that I and Steve Archer did studying the changes in the sea ice and its impacts on gas exchange. So first, let's get our bearings here. So we're talking the Arctic, the North Pole. No land, a lot of water, and sea ice, that's key. And not penguins, but polar bears. Very interested in you and your stuff. So why study the Arctic? It might seem remote, but it's actually a critical part of our global climate system. And it is experiencing the impacts of climate change at a much more rapid and intense rate than the rest of the world. In an environment dominated by ice, you can imagine a change in just a few degrees can have some profound implications. And so what we're experiencing is something that's transitioning from this into increasingly something that looks like this. This is a picture I took at the North Pole in August 2020. And so just to zoom out a little bit here to see the scale, this is a satellite image of the North Pole area. And you can see the yellow line is the median ice extent between 1981 and 2010. And the year you're seeing here is 2020. And so right away you can see it's striking how much of that white surface has been, very white reflective surface has been replaced by a dark blue energy absorbing surface. And that ice cap that acts as a barrier between the atmosphere and the ocean is now gone, increasing a lot of interaction. Okay, so how do you get up there and study this remote area that you can't navigate in the winter? We actually borrowed a play from Arctic explorers over 100 years ago, whose basic philosophy was, if you can't beat the ice, join it. So the Polar Stern, the German research ship, sailed up in the fall of 2019 and froze itself in the ice. And then you can see this bold line here, kind of drifted along. These different legs are the different legs of the expedition. Finally popping out between Greenland and Svalbard in late July of 2020. And so you can see here, this is a drone image, and at the bottom, this is the ship, this is the Polar Stern, actually kind of affixed to an ice floe right here. And so what we did, this little caricature here, is we set up different workstations on the ice. So we have the ROV City, that's a little submersible here that went out underneath the ice and measured ice depth in all parts of the ice. Ice City, where scientists were drilling, coring, taking ice samples. Ocean City, where they're profiling the water below. And the meteorological city here had tower and all kinds of instrumentations measuring composition of the atmosphere, temperature, wind speed, you name it. So what it kind of looks like from the ship, every morning we'd have a meeting, we'd go out, look for polar bears, lower that ramp down, get all our stuff, and then fan out all over the ice and begin our work. And this is the instrument that Steve and I built. We affectionately called the Tracinator. and it measures gas. Specifically, you may have heard of carbon dioxide and methane, very important for climate change, and one you may not have heard of, dimethyl sulfide, also very important for atmospheric chemistry. And so overall, the different topography of the ice, and here in this open lead, we're measuring the gas transfer, the gas exchange. And so I'll very briefly touch on what we found. So this is a graph because I'm a scientist and I can't help myself. This is a section of the ice. This is the ice here. This is the lead, that open water you saw the funnel on, snow-covered ice, and those frozen melt ponds of this column here. And what the takeaway from this should be is that you see pretty immediately that there is a flux of gas, I should have said this up front, of carbon dioxide from the atmosphere into the water. And so you can imagine in a melting Arctic that this is going to have profound implications throughout the region. So I really can't do this justice, but this is the PSA for this expedition that we're now just beginning to wrap up and produce data that's really going to inform a generation of Arctic research. And with that, I will conclude. Before the
How long were you out there?
I was out there for 3 months total, 2 months on the ship. And Steve was out there for a combo, I think, about 5 months.
So how did you get on the ship?
So the logistics of this, if we back up, so the polar stern was supported by other icebreakers. So there was resupply. I went too far. Resupply at these legs. So another icebreaker would kind of constantly be either coming back or out to refuel and resupply with personnel. Yeah. Logistics are incredible.
So can you explain why that dimethyl sulfite is such a critical
Yeah,
component?
so dimethyl sulfide is important because it's the major biologically produced sulfur gas, and it forms aerosols in the atmosphere that are important for cloud formation. So in the Arctic, where there is very little particulate, an increase in DMS could potentially have a big impact on cloud formation and other kind of chemistries. I think we got one.
What does the machine you built do exactly?
What it does is, let's see, go back here. So you might be thinking, hey, is that a cooler you could get from Walmart? Yes, it is. And Home Depot. But inside of this are tens of thousands of dollars of very sensitive scientific equipment. And what it's doing is it's pulling air in at the top of this funnel. The air is circulating in that funnel and going through these analyzers in the boxes. And we can determine the concentration of the gases either coming in or coming out of the surface it's measuring based on the differences of the inlet and the outlet. So that's kind of how it works.
Can you trace any specific effects in the last 10 years of that disappearing ice, and can you preview what will happen in the next 10 years? Will the pace increase or decrease or anything?
Yeah, specifically. I mean, it seems like we're in a feedback loop, if that's what you're getting at here, where more exposed water will absorb more heat, will melt more ice, and so on and so forth. It seems that is the trend that things are going.
So did you say that carbon dioxide comes from the atmosphere into the
That's right.
water?
Yeah.
And so that seems sort of opposite intuitively that I would think. So why is that? Because that means less carbon dioxide in the atmosphere. So is that why is that bad?
It could be bad because there's another process you may have heard of called ocean acidification. And so the ocean may be a sink for carbon dioxide, but that is at the expense of the chemistry of the ocean. And so as the ocean grows more acid, particularly small organisms that depend on fine balance of pH are going to struggle to survive. And the inverse has happened during different events. The ocean can then emit more CO2 as well. So it's not great either way.
How did you manage the polar bears in your research, and what impact and how did you accommodate them and let them live the way they should live?
So we did a lot of training for polar bears. Yeah, they were very well behaved. So we had professional bear guards with us. So when we were out on the ice, we had spotters kind of at the perimeter here, we had this area we called the Central Observatory. So we had people out on the ice with us. We had a bridge watch the whole time. So the number one thing is, as soon as you see the bear, keep an eye on the bear and then just leave. So you want to just not encounter the bear. And that's back how we managed the bears. But they did find us, and so we had to evacuate the ice every so often. And the first time you're like, oh my God, a polar bear. And then the next time you're like, oh, bears again, and they got to go back on the ship. Yeah.
What inspired you to get into this work?
Well, I did not. This was I was extremely fortunate to get on this. I guess it was a circuitous way, just understanding ocean microbiology is how I came to it, and biogeochemistry of carbon dioxide, methane, and now DMS, and wrote a proposal, and it got accepted. So,
But how did you get into it before that?
You mean joining Bigelow, or?
Like when you were little?
Oh. I was like, I want to build a cooler with I think it's just, I guess I've been interested in environmental science from the get-go, just base interest in the natural world, and I've been fortunate to kind of find a path in a career to keep doing that, so. I will plug, there is a PBS Nova documentary about this called Mosaic, so if you guys are into that, check it out. Thank you.